Hello, good morning, good afternoon, and good evening to everyone who's tuning in. Hope you're doing well and staying safe. On behalf of BioPetro, Arab Oil and Gas Academy, Arab Guru, SPE Egypt section, I'd like to welcome you all for our today's webinar in reservoir modeling. I am Mayar Tore, third year gas and petrochemicals engineer student at Alexandria University, and I'll be your moderator for today. Before we start, please, I'd like to remind you to drop your questions in the Q&A section below and to keep the chat box professional and ethical. Now, without further ado, let us give a warm welcome to Dr. Hatem Farouk. Dr. Hatem Farouk has worked extensively in oil and gas industry in both technical and managerial positions with local and international companies such as GAPCO, BP, and currently with Perenco North Sinai Petroleum Company, where he is the exploration general manager and board member in its JV. He received bachelor, diploma, master's, and PhD degrees in geology, petroleum geology, and geophysics. Dr. Hatem has taught industry-tailored and university courses as well as published and reviewed several research papers with local and international journals. In addition, Dr. Hatem supervised and refereed many PhD and master's programs. Dr. Hatem is a board member of the Egyptian Geophysical Society and active member of SEG. Thank you so much, Dr. Hatem, for coming today, and the mic is yours.
Thank you, Mayor.
Thank you.
Hello to everyone. I wish all are safe and doing well. Today we will spend almost an hour with such an interesting subject, which called the geologic modeling or reservoir modeling. So we'll start with the content of our lecture today. So we'll start as usual with an introduction. This will be followed by answering some questions like what's geologic modeling or reservoir modeling? What are modeling used for? What are model inputs and outputs? What are modeling steps? What are key planning issues? And then we'll understand how to build the structural and stratigraphic framework and Facies modeling, rock property modeling, and then evaluating the geologic models. And by the end, we incorporate the feedback. And after that, I will summarize to you what are the key points for the reservoir model. So as an introduction to the geologic modeling, geologic modeling or geological modeling or geomodeling or reservoir modeling is applied science of creating computerized representations of portions of the subsurface based on geophysical and geological observations. These geological and geophysical observations actually collected from either from surface like the 3D seismic or from the subsurface like the well logs and core data, and also from the outcrops, as we are gonna see, using a geologic concepts, and then from the field and well performance, we end up with the geologic model for the subsurface. So what's the geologic modeling? Geologic modeling is a discipline based on data analysis, synthesis, and above all, integration across disciplines. Geologic modeling or reservoir modeling is recognized as a critical technology, actually, and it is called the static modeling. If we are using the geological and geophysical data on. The geological model is the only place where all data and interpretations come together into a single numerical 3D model. Appreciation of the strengths and limitation of the various inputs is key to properly integrating all the data into the model. All geologic models are to some degree stochastic, and we will understand what it means by stochastic. Our reservoir, have a lot of heterogeneity, and because of that, instead of using some deterministic methods to build our model, we use these what we call the stochastic or geostatistical methods to build or distribute our property within the model itself. So the process of integrating all geologic, geophysical, petrophysical, and interpreted or conceptual information about a reservoir into a single numerical 3D stochastic model. This is the answer to the question, what is geologic model? So we continue to answer the question. So the geologic model actually is a 3D grid built from subsurface horizons, interpreted from seismic, for example, and faults. The 3D grid the 3D grid defines the geometry and structure of the reservoir. Each cell in the 3D grid is filled with a series of properties such as porosity, permeability, water saturation, shale volume, depositional facies or lithofacies. I will understand the difference between both, and the fracture density, for example. Typical dimensions for a geologic model cell are about 200 feet by 200 feet by 1 foot. Or it depends actually on which stage you are using to build your geologic model. So these dimensions are not standard. You can change it actually. Depends on the amount of data you have and how detailed the data you have. To combine all of these properties together, we must integrate all the different data types, like the tops of the formations, sequence stratigraphy, a discipline or interpretation, the stratigraphic correlation, and so on. So what are the model or the reservoir model used for? Actually, the most common usage of geologic models or reservoir models is to provide quantitative 3D numeric input to reservoir simulation. But there are other uses as well, actually. So we use it as an input to reservoir simulation, or also it provides capabilities to calculate volumetrics, 3D volumetrics, actually not 2D. So 3D volumetrics is very important to understand the hydrocarbon initial in place. Most of the modern geologic modeling applications contain some well path planning. You can plan your well path to reach the target. Having both the structure and the stratigraphic framework, this enables us to make what I mean a prediction about the faults, and are these faults sealed or non-sealed? We'll talk more about faults in the next slides to understand it, because this is very important in the production time scale. So you can identify the faults. Also, we use the model for reservoir surveillance and to visualize a full field fine scale geology, actually. So these are the usage of the geologic model. So what are model inputs and outputs? What I'm going to input to build my model, and what I will get from out from my model. So different data types and interpretations are required actually to incorporate into geologic models. It is obviously very diverse input that intended to give you a feeling for the scope of the integration challenges in building geologic models. So The input will be, or I will summarize the input to you in three main categories. The first one is the interpretations and the prediction derived from seismic data. And the second one is the information we get from interpretations of logs and core data. And the last one is conceptual or analog data. So the last category is often the least well appreciated by non-actually modelers. So what I'm gonna gain from, or what are the outputs of my geological model? The first and most important one is the volumetrics, either gas initial or gas in place or oil in place, the aquifer size. Also, you can see the 3D distribution of net pore volume, continuity of the net pore volume, and fine scale permeability structure within the connected pore volume. And then the fault transmissibility. You will notice that we talk about the fault several times. So what are the modeling steps? So there is a standard flow to all modeling projects actually. So we have to plan to our project or the modeling, the reservoir modeling project. We have to have our plan. We have to assemble the resources we need and the data we need to the project. And the resources are not data only, but also the geoscientists that they are gonna build the geologic model, either geologists, geophysicists, petrophysicists, and from different disciplines, actually, the petroleum system analysts, and so on. And then we build the model framework. This will be followed by building the Facies model, then the rock property model, and then quality control and evaluate our model, and then use the model, okay, to calculate your volumetrics, to find out the places to drill, and so on. And by the end, the modeling is actually a team effort. It's not a single person effort, it's a team effort. And again and again and again, it is team effort because no one knows everything actually. So let's talk about the structural framework. So building a structural framework involves using both structural and stratigraphic surfaces actually. So one approach was to take a set of depth converted 2D grids of fault traces, for example, and seismic data, and build a 3D framework. So we started from 2D and then built a 3D. This was in the old days, actually. But this is a slow, what I mean, application, but a better 3D solution where we take the horizon and fault interpretation in time and import them into the geologic modeling application, along with the velocity interpretation to convert time into depth, as we talked in the previous lectures about that. We built a 3D framework in time, and then depth converted the entire framework into depth using a velocity model. So the 3D framework includes both structural surfaces and reservoir stratigraphy. And we convert the 3D framework again to a 3D grid by filling the framework with empty cells with a defined internal laying scheme. What I mean, if your data does not fill all cells within your model, you will add some empty cells just for the sake of regularity. We mentioned faults several times, and even here in this slide. So why faults matter? Actually, the petroleum industry uses subsurface flow models for two principal purposes: to model the flow of hydrocarbons into traps over geologic time and to simulate the production of hydrocarbon from reservoirs over periods of decades. So faults can create actually compartments if they are sealed. So you will have different compartments. If you have reservoirs that is faulted, so and these faults are sealed faults, you will end up with compartments. So if you drill a well in one of them, you will not produce the rest of the hydrocarbon in the other compartment. Faults are actually three-dimensional. It is not two-dimensional as we see here. But actually, they are approximated on both modeling application as planar membrane or whatever. The point is that I want to show to you that faults can be like sealed to compartments, our reservoirs, and also if it's not sealed, it will be like a flow connector. Okay, so you can have the hydrocarbon, what I mean, move across these faults. So it affects the flow path of your hydrocarbon. Because of this, they are very important. Faults are very important. So they are not simple like what we plot here. Faults are structurally complex, actually. They are consisting of a core and a damaged area. So it's a zone. So the fault is not just a plane, it's a zone of damage. And actually it depends on, it can seal or permit, as we see, the fluid, and it to be a sealed fault or a non-sealed fault, it depends on several geological processes, like the degree of degradation, for example, the dissolution, cementation, and mineral precipitation or deposition. If you have breccia, if you have calcite, and so on. It depends on the stress state of that forms the faults themselves. So we can talk actually a lot about faults because they are controlling our subsurface. Also, they can enhance the flow, of course. So we'll talk now about the stratigraphic framework. So the stratigraphic architecture is very important because it identifies a geological control on fluid flow. So we need to know our stratigraphic succession, and as we mentioned in the previous lectures, that we use the sequence stratigraphic branch of geosciences to understand the relations, the stratigraphic relationships between different layers. From this, we can understand the lateral and vertical porosity and permeability, for example. So the stratigraphic relationships are very important because they establish the connections and barriers between reservoirs. So it gives us context of communication over geologic time. It identifies it as the flow rate or affecting the flow rate or the communication about the production time. So because of that, they are very important, and different considerations that we can get from the stratigraph, which is the thickness of the layer of the individual stratigraphic units, the relationship between stratigraphic units, and the juxtaposition of different units against each other, and the distribution of shale beds, for example. Shale is seal, and on the same time it's a source. So the stratigraphic framework is very important because actually it defines the flow in the subsurface, and from the sequence stratigraphic, we can understand the nature of the surface. These are erosional or depositional, or we have onlapping, truncation, progradational sequence, and whatever. So going after that for the facies, as we're talking about the stratigraphy, and facies ideally is a distinctive rock unit that forms under certain geological conditions, for example, different sedimentations, and this reflect particular process or environment. So if you take a look, for example, on this figure, which is for a carbonate facies. So this is how it looks to understand the word facies. So this is, if you have carbonate rock, you will see it like this. And if you have, for example, a marginal marine siltstone or sandstone, it will appear differently, as you see. So you can now differentiate between the two facies. You will understand that this is carbonate facies because it has its own color. It's a white color, for example, and there is no stratification, for example. But for the siltstone and sandstone, you will have stratification, and it has yellowish, brownish color. So this is facies. And what I'm talking about facies now, it is depends on lithology, for example, because this is carbonate and this is sand and silt, and this is what we call lithofacies. So facies can be subdivided according to what you are using facies for, the nomenclature for. Are you split your facies according to lithology? So it will be a lithofacies. If you divide or subdivide your rocks according to paleontology, so it will be a biofacies, and so on. So it depends on that. So facies is very important because it is what I mean, know or understand the type of rocks. You will understand its porosity and the effect of the mineralogy within each facies to on your reservoir. So let's ask ourselves on the facies modeling. Why model facies? Why we are modeling facies? And this is what I try to introduce to it now. So a given facies is both mappable, so it covers an area that could be mapped, and distinguishable, as we saw on the previous slide, from surrounding facies. So as we mentioned, I will repeat again. So you saw the carbonate facies, you saw the silt and sandstone facies, and how they are look different. For modeling purposes, the facies are usually defined by distinct porosity, permeability distributions that allow unique and important flow units to be described. So I will describe my deposition process and how they are connected to each other, my flow, how it will, what I mean, how can I describe my flow unit within the subsurface. Facies also tend to have unique geometry and directional characteristics. So the knowledge of this can be powerful predictive tool when distributing facies in the field, for example, with poor well control. So what I mean, I can expect if I don't have a lot of wells or I have sparse wells, so if I understand the facies, I can know the extension of the facies and understand where is my porosity goes, in which direction I have better porosity, I have better permeability, because permeability depends on porosity to a great extent. So the facies is very important because it controls the spatial distribution. Actually, we can have facies have the same age but different lithology or whatever. So facies are very important. We model facies because we use this to distribute our porosity and permeability within the reservoir model. Also, we use seismic data for facies analysis. So we can, and we call it seismic facies. So we talk now in these two slides about the geological facies, okay? And we mentioned that we have different types of facies. Actually, it depends on how I'm subdividing them. If it is lithology, it is lithofacies. If it on paleontology, it is biofacies. and we understand the importance of the facies that affect the distribution of porosity and permeability in my model. So if I don't have enough geology, because the input of the geology is from the wells, so I can use seismic, because seismic covers more area, and I can use what called seismic facies. So, and we run what's called seismic facies analysis that makes use of different seismic parameters in order to get other than structural information. You can interpret seismic as you want, okay? But in seismic facies analysis, we interpret the seismic to identify or to find out the different facies that I have. We should take into consideration when we do seismic facies that how the reflections look, how the amplitude look, what is the dominant frequency of my data, the reflection polarity, the interval velocities, the reflection continuity. All of these are used to the geometry of the seismic reflections themselves. All of this can be used to identify the seismic facies. And we interpret this by the aid of geology. If I have even few number of wells, I can start to understand the lithology or whatever the type of rocks per each facies. And we have like the flow as you see on the screen, and understand the pattern of the reflections, and then tie this to the environment of deposition. So you can see that, yes, I have here a slope deposits, but and here I have like a shelf edge, a reef, and I have carbonate shelf. So let's see the output of seismic facies analysis. Actually, we can get either vertical sections or maps. So let me show you a map after we finish the interpretation and prediction from the seismic analysis. So if you have like a contour map like this, after you finish the seismic facies analysis, you can distribute the depositional environment, so we can identify that this zone is full of non-marine deposits. This zone has marginal marine deposits. This zone is a slope deposits, and this zone is characterized by basinal deposits. So I can use the seismic facies analysis now to build my reservoir modeling or my subsurface geologic model, and distribute my facies or my facies depend on the seismic facies on the subsurface. So we can use different methods actually, or different ways to model our facies within the reservoir, within the reservoir modeling itself. So the two main are either deterministic or stochastic, as I will mention to you. So deterministic facies are often integrated with the aid of seismic data, and can represent depositional, lithologic, or diagenetic features, geologic features, of course. These interpretations are imposed on the model in the form of maps or 3D elements, so that the cells contained within a facies are assigned properties like the lithology. This is sand, this is carbonate, or the porosity or permeability or whatever. So we put the constituent of each facies within this part. So I use here for the deterministic facies, I use seismic data, for example. Okay, but many facies element cannot be interpreted as distinct features in seismic data. Each tool has its limitations. So if we mention that if I have sparse wells means that few number of wells, so I will not be able to cover the whole area of my modeling, but I can use seismic to cover more area. What I mean is seismic is also has limitation. So for the facies that I couldn't use seismic to interpret it, it is recognize that there is some uncertainty as their exact location within the reservoir is not what I mean very well defined. So in this case, I will use the stochastic facies, and the stochastic facies is our stochastic technique is we are using some geostatistical approaches that can estimate and calculate the distribution of the facies I have. So I use in stochastic facies, I use different computer programs, and mainly we use what's called the geostatistical facies modeling. From this, we can know the distribution based on the relation. We find out the relation between the seismic data, for example, and the well data, and from this, we can distribute that based on equations or based on statistical techniques which were tweaked to serve the geoscience. Because of that, it's called the geostatistics, and the method is called the stochastic facies distribution. So we can use, to distribute facies in my reservoir model, it depends on the type of data I have. If I can have from wells and seismic data, I can use the deterministic method. If the facies are not easily defined on the seismic, I will use the stochastic facies distribution, and also I can use the geostatistical facies distribution. Also, as I mentioned at the very beginning, or on the second slide, that I can use in reservoir modeling or in geological modeling data from the subsurface and the surface. And we mentioned from the subsurface is the logs from the drilled wells, and from surface you can use seismic, and also we can use the outcrops. And the outcrops are the exposed rocks. Because of that, the geoscientists arrange field trips to see the distribution of the rocks and the structure relationship and whatever. So if I have outcrops nearby the areas that I'm modeling, so using the outcrops will be of great benefit to me when I build my model. So the outcrops, for example, this is an outcrop of an alluvial fan. You see, you have a mountain and you have an alluvial fan, the parts that have the gray color, and this is how when it is solidified or whatever in the rock. So you can see from the outcrop all the type of rocks, as you see, with different colors, which is different facies, yes. And you have also a different facies for the fan itself, and you see the geometry of the fan, how it is distributed. So the outcrop analogs, you see analogs because it represents a subsurface. I will have this repeated in the subsurface. So it provides qualitative and quantitative descriptions actually of the external large-scale stratigraphic architecture for use in well log correlation and in defining the zones to be modeled. Actually, this is provide a lot of information, like understanding the geometry of the rock to each other and the geometry within the rock itself. If I have cross bedding, if I have whatever, so I can know even the texture of the rock itself. So I can use that in the subsurface when I model my facies or distribute my facies across the whole model I have. We can use actually different tools that I'm going to show you next. So after that, we'll do our rock property model. And rock property modeling is actually used to improve the understanding of the hydrocarbon distribution for volumetric analysis for the reservoir and understanding the flow within the reservoir. There are two sources of rock property actually. which are the logs and the course. Okay, and to build my property model or to build my rock property model, I need to know what are the most common properties that I need to model. They are the facies, the total porosity, the horizontal permeability. What also is important are the water saturation and vertical permeability. So the rock and fluid properties that are measured, including porosity, water saturation, permeability, porosity, and porosity permeability relationship, also the capillary pressure, the mobility, all of these are called the rock property modeling. So anything that can be expressed numerically, any piece of information, any piece of data that can be expressed numerically. Why I said numerically here? Because as we mentioned at the beginning, our model is a numerical model. So we put all the geological and geophysical information to build a numerical model. So when you have your model, you put just your mouse and you will read whatever the porosity, the permeability, the water saturation, the hydrocarbon saturation, any type of properties that you need to know. So this will be the final output of my model. So let's see how we model our porosity. Porosity is directly tied to the facies. And we mentioned when we talk about facies that facies is important because it gives me the way of distributing the porosity and permeability within the subsurface model. So generally speaking, porosity is tied to facies. Sometimes we also use local modification based upon seismic facies, as we mentioned, and diagenetic facies. So methods used to populate the models, populate means that distribute the porosity, or populate is putting the porosity values in each cell of the model. So we can use a deterministic method, and which is a much easier way, is because you have wells, and in wells you acquire or you log a porosity log, so you can calculate your porosity, and then you can distribute between wells. But as you see that the deterministic, what I mean, will give you very smooth model, actually, because you have distance or long distance between the wells, as you see. So you like interpolate the values between the two wells. So how can I do this, or I make this more realistic and obey my data, which is the seismic data, for example, in the area? I will use the stochastic modeling, because the stochastic covers the uncertainties. It solves the uncertainties in between these two wells. So suppose that I have these two wells, as I mentioned, if I use a deterministic way, I will take, like, for example, if I have a value at well 1 for the porosity is 20%, and the at well 2 and on the same depth, the porosity is 30%. So what you expect the porosity in between will be about 25, okay, because I took the average. So it is very smooth. I just take arithmetic average or mathematic average or whatever. But in the stochastic, it uses geostatistical, use different ways, variograms and whatever that you are going to show, histograms, variograms, and so on. And it finds the relation between the well at the well location, the reading at the well location, with the seismic data, and you know that the seismic data is built up initially from density and velocity. So it finds a relationship and then start to apply this relationship on the seismic traces or seismic samples in between the two wells until it reaches the other well, and you will find the value is the same like the well, and so on. So because of that, the stochastic is preferred because it covers all the uncertainties in the distribution or the population of the models. So, and at the end, as I just mentioned, you will end up with your model, subsurface or reservoir model or geologic model in general, but we prefer to use the stochastic models for the stochastic methods for the reasons that I just mentioned to you. So let's talk about also again about the porosity. So what are the inputs that I need for the porosity? We need well log data because this is a direct measure. What I mean, you know that you can have like sonic log, density log, and neutron log, and each one read the porosity by different way. But you need what I mean, the wells, because the wells are reading like every 0.1 meter or 0.5 feet as a raw data from the well. And then you can blocking this, what I mean, these values to fill your cells, and you have like a vertical scale of this modeled cell. You can use after that the histograms, for example, to show the distribution of your porosity. Also, we can use the valuegrams. And we call the property variogram, and the property here is for the porosity. So valuegrams and histograms are a method of distribution for my porosity within the subsurface, and we can define the relationship to facies, the porosity to facies. Okay, and you start to populate the cells of the model with your porosity. So you have the facies, and you have the relationship from you start from the well, and you have the distribution of your porosity through histograms and valuegrams, and you find the relation with the facies, and then you populate each cell with porosity value. So if we talk about porosity, so we should talk about permeability, because permeability is very important, and you understand what are the different. Actually, also in populating or distributing permeability within our subsurface model, we have the two methods, either deterministic or stochastic. Which one will prefer? Yes, the stochastic, because it covers all the uncertainties of the deterministic method. So again, we'll have the permeability, the input from actually the main source of data for the permeability comes from the relationship between porosity and permeability, and you use valuegrams for this property, and you have what I mean. You can have the relation between porosity and permeability, and then you will go to the facies and find out the relation between the permeability and your facies, and start to populate the cells according to the facies distribution. So we talk a lot about facies. So facies modeling is very important. Actually, it is of crucial importance. After that, when if you drill wells, okay, so you will need to integrate your production data with the well, your production data and well test with your model. So this will be updating. So if you start your model before drilling and you use this model to identify the drillable location, after you drill your wells and you run well tests, you will come up with some data and updated information. You have to update your static model or the geologic model or the reservoir model, actually by the fluid flow information that you gain from the well test. So from this sort of information, you'll have the permeability thickness and the average permeability at the well. You will have evidence of large scale about the permeability. So you get more information about permeability, which you use actually to put permeability from the beginning. You use the relation between permeability and the porosity. But when you have well test, you will have real measurement for the permeability. Okay, and you understand more your reservoir. So you will update your reservoir after distance. So far, as we mentioned from the beginning, so any piece of information for the subsurface is very important to make value to your subsurface model. Then we need to evaluate our property model. So we'll ask ourselves, or quality control, do well tie. If I have well now with the seismic data, and I use the stochastic, for example, methods to do the population and whatever, and the distribution of the petrophysical parameter or the reservoir parameters and the facies. Do well tie if at the well, which has logs that measure directly this porosity or whatever. Do I have the same value of the porosity? This is from what's meant by do well tie, also the formation topcycle, because I'm using horizon from the seismic data. Okay. Are rock properties sorted by facies? This is correct or not? Are well data owner in general? Does model property distribution match the input distribution? Is visual appearance satisfying the tool I used before, like the variogram, for example? So I have, for example, as you see, the histograms and the relationships and cross plotting to understand what I have, do what I have, do what I built. I build in the model match at the well location. So wells are very important because they are not only used to take the hard data from them. Hard data mean geological data and logging data, but also they are very important because I use them for the quality control on my output or my models that I build. Okay, because I use other methods than the deterministic method. Then I have to incorporate a feedback. So incorporating a feedback, which is a key part for the modeling process, actually, it is rarely used, but it is very important, actually, that you incorporate the feedback after you drill and get some updated parameters, and you build, for example, your dynamic model, or you have simulation models to come back and feed to your static model and update it, and which with all type of data that you can be insert or update your subsurface model. So the model, the reservoir model or the geo model, it is not a rigid model, or you build it once and that's it. No, you keep, what I mean, updating it as much as much as you have data. If you have new data, you have to update your model again and again. And so it is, yes, it's called a static model, but you can update it with all the information that you have, that you can collect or you can have after drilling or whatever. So generally speaking, what I want you to remember are that models are a collection of cells or boxes filled with numeric data. So we change all our geological and geophysical data into numbers or into numerical data or digits or digital data, and we fill these in boxes, which are the cells that I build my model with. Modeling is a team effort. No one can build a model by himself alone. Models should be fit for purpose and carefully planned. What I mean by fit for purpose? Do I build my model at the very beginning in a new area, so I have very few number of wells, or even I don't have wells? So what is the reason that I build this model? Okay, to understand where are the basins and where are the highs. So this is, I should build my model for that purpose. If I build my model to identify new locations for drilling, so I have to use a lot of data to enhance this or to facilitate this. So most models built as input for fluid flow simulation models. This is what I want you to remember again. A good model captures the reservoir's key flow characteristics. Stochastic methods are preferred for distribution of rock properties more than deterministic. Why? Again, deterministic is very smooth because it is built on very simple averaging of the data, but the stochastic, what I mean, use up to date mathematical or geostatistical approaches to distribute my data and cover the uncertainties of the deterministic method. So what are the main steps in modeling? Just to remind you, the stuff, you remember the resources, the stuff and the planning of the project. You need to gather and QC the input data. You will build your framework, both. You remember the frameworks? Yes, structural and stratigraphic, and you know the reasons for both. We build the Facies model, which is very important for the property models. Because of that, we build the Facies model at the beginning and then the property modeling. Then I evaluate my model by quality controlling, as we mentioned, and then I will use my model for like fluid flow simulation, for well planning, for volumetric calculations to understand fault seals and whatever. So again, I want to repeat this again. This is what we're doing to build our model, and these are the steps in turn, what I mean. One after one. At the beginning, I should plan very well. I should staff my team with experienced people of different disciplines. Then I should gather all the data that I can and the quality control this data, and then build the structure framework, followed by stratigraphic framework, followed by building the Facies model, then building the rock property model, then evaluate my model and the quality control it. And then I use my model for the purpose that I built the model for. With this, I conclude my presentation, and I'm ready to answer any question you have.
Thank you so much, Dr. Hatem, for this super informative webinar. I can't see any questions till now, but if there are, we're waiting. If anyone please have a question, don't hesitate to drop it in the Q&A section. How can we estimate rock properties from seismic velocities?
From what I mean, we use seismic Facies analysis, not the velocity itself. I use the seismic velocity to convert my input from time into depth. So we mentioned that we can use, for example, when I build my structure framework and stratigraphic framework, I can start by using seismic interpretation, okay, and input this to my model in time, because you know that seismic data is recorded in time. And I can use the velocity to change this time, this data that is in time, into depth, because my reservoir modeling or subsurface model or static model should be in depth. So this is where I use my velocity or the seismic velocity. So I use seismic velocity to convert the structure model or the maps that I use, horizons and faults from time to depth. But for Facies, I use seismic Facies analysis, in which I interpret my seismic data according to the reflectivity pattern, the amplitude distributions, the frequencies, and start to split them into seismic Facies. Seismic Facies means that this part of the seismic data has its certain characteristic different than this part, different than this part, and then I can find the relation for each part of this or each seismic facies of them with the geology to understand that this reflection represent, for example, sand silt facies. This is represent, for example, carbonate facies, and so on.
Thank you, Dr. Hatem again. And
Thank you.
now to highlight, this session has been recorded and will be uploaded soon on PyPatro YouTube channel. So kindly make sure to subscribe on our channel. Wishing you a great day and bye.